Okay, in this video we're going to have a very quick canter through some of the basic electronics, speed electronics, just so you can make sure that you're happy with some of the voltage, current and resistance and series and parallel circuits. So with all of this, I'd make sure that you've got your formula sheet available and you use it. So first of all, we're looking at branch A. So branch A there. So our total resistance on there. So resistance of branch A is just going to be R1 plus R2. So we've got 45 plus 27 plus 33, which is 105 ohms. Okay, so now we're looking at the total resistance of the network. So we've got 105 ohms just here in parallel with 100. So we've got looking at our formula sheet again, 1 over our total resistance equals 1 over R1 plus 1 over R2. So we've got 1 over 105 plus 1 over 100. Okay, what does that work out to be? So that equals 41 over 2100. That gives us 51.2 ohms. Happy days? I beg your pardon, that doesn't equal that, does it? So therefore then that's our 1 over total resistance, so RT is equal to 51.2 ohms because I've taken 1 over this. Okay, we're looking at the voltage across branch A. Now if I say, well, if I put a voltmeter here and said what does that voltmeter read, you would say exactly, you'd say 6 volts. So you know, if I was to put now my voltmeter just there like so, to read across, is there any difference? No. The voltage across a parallel network is exactly the same. So the voltage across point A is 6 volts. Okay. So the current going through branch A, so we use our formula sheet now, just shrink that down slightly. So current is equal to voltage divided by resistance. So now we've established that there is 6 volts across it, and the resistance of branch A is 105 ohms. Therefore, we know that it's going to be 57.1 milliamps. 57.1 times 10 to the minus 3 amps. If you can't remember that minus 3 is milli, then don't worry about it. And total circuit power. Now with lots of formulas to working out power, so we look on our formula sheet. If you don't need to work out any more, then don't. So we know that the voltage across our circuit is 6 volts, and we know the total circuit resistance, so let's just use that formula. So 6 squared over 105. Okay, what does that equal? 703.125 times 10 to the minus 3 watts, 703 milliwatts, 0.7 of a watt. However you want to write it, just write down what your calculator says. Okay, so a conductor has a resistance of 12 ohms. That's our original resistance at 20 degrees C. Then it goes up to 17 ohms at 30 degrees C. So I'm going to write down the formula for this. So I'm looking on my formula sheet for anything to do with temperature coefficient. And what have we got? There we have. So we've got change in resistance over our original resistance is equal to the temperature coefficient multiplied by the change in temperature. So we write down what we know. So the change in resistance is 17 minus 12. So we could just write 5 down there, but I like to spell it out. Divided by 12 is equal to the temperature coefficient multiplied by the change in temperature. And the change in temperature was 30 minus 20, so 10. So just tidying that up a little bit. So what we got, 5 over 12 is equal to temperature coefficient multiplied by 10. How do we get the 10 across the other side? So we're going to divide 5 over 12 divided by 10. Gives us our temperature coefficient then is 1 over 24. And I can just leave it like that. Okay. So we've got a circuit here, 120 watt output power for the motor. We want to know what the input power is. Power is equal to I times V. So we've got 5.5 amps multiplied by 24 volts gives us 132 watts. And it makes sense if you like. This question could go on to calculate what the efficiency is, but you're never going to get out more than you put in. If you do, let me know, and we can obviously share some of that idea. So 132 watts to make a 120 watt motor spin. Okay, because it's not efficient. Okay, and then the last question we've got on these is, without any scaffolding, we just want to know what the power dissipated in the circuit is. So we need to do some simplification. So the first simplification there we need to work out is that 2k plus 2k is 4k. So then we've got a 4k in parallel with a 12k. So we've got 1 over, so our parallel network, 1 over 4k plus 1 over 12k equals 3k. Okay, now there's no harm in making drawings, so now we've got 3k, which is all of this. That's 3k in series with a 1k. So that's our circuit. So the good thing about drawings, it explains what you're doing. So now we need to know what power is. So some of you might say, oh, well, let's work out what current in the circuit is, and we could work out what current is, but we also know that power equals voltage squared by our total resistance. So we know we've got 12 volts squared divided by a total resistance of 4k. So that's going to give us 36 milliwatts. I did say it was fast. How was that?